lots of interest around the Internet of Things at the moment. There are a number of competing radio technologies. The radio technology that caught my interest is LoRa. You can get hold of LoRa modules quite inexpensively now. Here you can see one that's made by eByte. You have an interface on there which is an SPI interface. Of course, how you approach this really depends on your experience and what you have kicking around the lab. For me, the easiest thing to do is just plug an FPGA straight into the SPI interface and plug the same FPGA into a PC, so I can get easy access to the device. I used an RTX-7 development board to do that. Straightforward thing to do. And then when I wanted to look at the transmitted signal, I used a software-defined radio, which looks like this. So the hardware setup, we've taken the eByte module, which contains a Semtech SX1262, and we plugged that into a software-defined radio. We've also plugged the SPI side of the eByte module into an FPGA development board, which in turn is connected up via USB to a PC. So the SPI interface, which I popped into this FPGA, I wrote this little piece of software to make it easier to send the commands over there. This is what I use to control the eByte module. So this is the interface to the software-defined radio, so let's switch that on. And the next thing we have to do is set up the eByte module. So first of all, I'll set the mode, the packet type. It has to be done in this sequence in accordance with the data sheet. The frequency, the transmit power. This sets the transmit and receive addresses. This is just going to load some data up into the FIFO. The spreading factor, we want to make sure we can see this, so let's put the spreading factor at 12, turn the bandwidth down, code rate 4 and 8, and we'll turn the optimization off there. Preamble symbols, pop 10 on there. The header type will have that as the packet type will have it as explicit. We'll just pop 8 bytes on the payload, turn on the CRC and keep the IQ as standard. We'll set this up as a public link. The TCXO timeout, I'll just put high so it doesn't time out, and the timeout for the transmit, I'll just put high and tell it to transmit. There you can see the transmission being picked up and displayed by the software-defined radio. So let's change a few things on here. We'll drop this down to 1 byte so the transmission isn't quite so long. Send that packet parameter over. So the spreading factor, as we decrease the spreading factor, that's going to decrease the amount of time on air. And when you actually drop the spreading factor and take a look at the symbols here, what you can see is this gap has decreased. So it's got much smaller. So that's going to result in the time spent on air to transmit that data reducing. So we have this smaller payload. Let's set the spreading factor back to 12 and transmit. As you can see, the gap between the symbols here has reverted to where it was originally. So the device that we're using here is one of the simpler devices. It's aimed at the sensor side of the Internet of Things, so it's a good place to start if you want to get a feel for these devices. So let's change the frequency that we transmit at here. We'll move from 915 to 916 and set transmit and chase that with the radio, taking it up to 916, and there you are. The frequency of the transmitter has moved up as instructed. Here you can see the preamble. You can see the up chirp in the preamble there, followed by the down chirp at the end of the preamble again, and the data after that. So there we are. That's a quick look at a simple LoRa transmitter